Hi everyone, welcome and thank you for coming to the SETI Institute's Lunchtime Seminar Series. For any of you who are new, we have these every week with an amazing variety of fascinating and illuminating scientific talks on subjects that really span the range of astrobiology, from astronomy to geology to planetary science to physics to anything in between. And this week we are very lucky to have Laurance Doyle. Laurance he's one of the people who's been at the SETI Institute forever. He just told me he'd been here since 1987, which is pretty impressive. And his interest and experience spans the range of everything we do here, from his graduate work at the University of Heidelberg in Germany, where he studied the rings of Saturn. Then he's also worked on everything from quantum astronomy to animal communication, to right now he's a member of the Kepler science team looking for planets around eclipsing binary systems, to his talk today, which will be on historic solar eclipses. These are eclipses of interesting historical significance. So this should be a really fun and exciting talk. Just a couple of programmatic reminders. We do videotape these talks. If you happen to miss a talk, you can get it on our website. Just go to www.seti.org. Click on the picture of Frank Drake that says Scientific Lectures to get to the Colloquium homepage. From there, you can see videos of past talks. You can look at the schedule of upcoming talks. You can sign up for our mailing list to get notifications of talks. Also, while you're on the SETI webpage, you should check out our new Facebook and Twitter feeds. If you're on Twitter, you can get interesting scientific articles sent to you multiple times a day. If you're on Facebook, you can become one of our fans. You can see links to both of those on the SETI homepage. So thanks to everyone for coming. And please, if you can, try to hold your questions till the end when I'll come and bring you the microphone. That'll help capture your questions on the video recording so that future generations of people can hear your questions and not just the answers. So thank you and welcome, Laurance.
Thank you. 87, wow, time sure flies when you're having fun. Well, a couple years ago I went to an eclipse in Mongolia, and I thought I'd share some of the experiences. And also I was beginning to think more in terms of occultations, transits, and so on. And I am a member of the Kepler science team as a participating scientist, and there we're looking for transits. Those are kind of mini eclipses. But I'm going to emphasize Mongolia just to show you the basic idea here is an overview, and we'll take a little bit deeper look at one aspect, which is the Mongolian eclipse of, I think it was 1221. Okay, well, most scientists are aware of these, but basically an eclipse, there's been some nomenclature confusion with regard to the term occultation, eclipse, and transit. Transit's when a little thing goes in front of a big thing. Occultation's when a big thing goes in front of a little thing. Eclipse is when things about the same size go in front of each other. Now, for a while there, the Kepler team was discussing secondary eclipses when they meant occultations of the star in front of the planet detected. And when you have eclipsing double stars, that gets very confusing fast. The secondary eclipse refers to the fainter star being moved in front of by the brighter star. And if you call the occultation of the planet a secondary eclipse, you can get really confused. If you really want to be confused, I wrote a space.com article on nomenclature. We call planets B, so the name of the star system, B, is the name of the planet. But small case b is also the name of some other stars. So we have all sorts of B's and A's, and it's very confusing. If you want the whole schmagagus, then just look up on space.com naming new planets. Okay, so solar eclipse is interesting because the moon moves in front of the sun, and we can see the corona, which when you see it live looks like somebody shaking silk sheets. And it's basically a few million degrees, and that's the atmosphere of the sun. And you can pretty much only see it during a solar eclipse. That's the best time to study it. A lunar eclipse, so this is when the moon moves in front of the sun. Since the moon's orbit is inclined a few degrees, 5 degrees or so, from the orbital plane of the Earth, we don't get an eclipse every month. We have to wait for the nodes to line up, the places where the moon crosses going into the northern compared to the southern hemisphere. Now, a lunar eclipse is when the moon moves into the shadow of the Earth. And basically, the Earth is here, and the sun is here, and the moon moves into the shadow, and there's bending of the light, the sunlight, from the atmosphere of the Earth onto the moon. So the sunrise and the sunset light get bent to hit the moon, so the moon turns copper. Lunar eclipse was how Columbus saved his one of his voyages. He said, he was being held in a fortress, basically, and he said, I'm going to turn the moon to blood this evening. And so it turned red, and the Indians were very impressed and gave enough supplies to leave. And I think that's probably where Mark Twain got the idea for a Connecticut Yankee in King Arthur's court, who saves himself by a solar eclipse. A partial eclipse is when the observer is not in the moon's shadow, but in the penumbra of the shadow, and that looks like that. And this path, of course, is much wider. A total solar eclipse, where the stars come out and so on, is much darker. And then you can have an annular eclipse, and that is when the moon happens to be farther away and the sun happens to be close. So the moon doesn't exactly cover up the sun. Now, getting this exact fit is unusual. The moon is about 1/400th the size of the sun, and it's about 1/400th the distance. So that means the moon exactly covers up the sun most of the time. Otherwise, we get an annular eclipse or an occultation. And this hasn't happened. The moon's moving out about an inch a year from the Earth. So this perfect fit is something that our age gets to see, and that the dinosaurs would not have seen, for example. Other planets have eclipses, but they don't have the exact fit. The other trouble with Jupiter is you can't stand on the surface and watch an eclipse, because it doesn't have any surface. Now, the moon occults, moves in front of the star, in this case Regulus, and occultation occurs, and that's been used to measure that. A lot of science can be done by using the moon as an astronomical instrument. In addition to relativity, which we'll discuss later, as the moon moves over a star, you can get the diffraction pattern of the star if it has some finite size. So you can measure the size of stars, and a lot of stars in the plane of the orbit of the moon have been measured. Their sizes have been measured using occultations. A lot of science can also come from transits. Here's an example of Venus transiting the sun. And we know that with Kepler, this effect allows the detection of Earths. Now, Earths cannot be detected probably around sun-like stars by measuring the wobble of the star. And that's because a wobble measurement relies upon the mass ratio of the star compared to the planet. So it's kind of an R cubed, radius cubed effect. A transit relies upon comparing the area of the planet with the area of the star, so it's an R squared effect. That's why transits are more effective. If you can think of some way to detect planets that is a radius effect, just plain R instead of R squared, you'll be 10 times more sensitive. This is just an example of what the brightness variation occurs when the moon goes over a star. So you get this diffraction pattern because the star has some finite size. And you can fit that diffraction pattern and determine the size of the star. So in other words, the moon's been used as an astronomical instrument in many ways beside eclipses. This is a stereo image from the stereo spacecraft, and it happens to be 4.4 times the Earth-Sun distance. And that's what an eclipse would look like if you were a planet at 4.4 times the Earth's distance. So in other words, this is the moon, and this is it going in front of the sun, but obviously it doesn't produce the spectacular total eclipse. And an example of transit science is, of course, Kepler. My job for Kepler, which will be another talk, not this one, is we're looking at eclipsing binary stars. And basically those are double stars that orbit in front of each other along our line of sight. And if you plot the brightness with time, they produce regular dips as they move in front of each other. So this is a kind of eclipse that stars do all the time. If you have a planet moving in front of the two stars, you can get at least 2 dips as the planet moves in front. So while Kepler's looking for an Earth-like planet to go in front of a single star, it has to get 3 transits to confirm an Earth. We'll get 4 transits actually, in 1 orbital pass. So eclipsing binaries are a good target, I think, even to find Earth-like planets. And maybe that'll be a talk later. Okay, somehow a kind of jewelry motif emerged when it came to naming eclipse effects. Excuse me, as the moon goes over the sun, the light shines through the valleys of the moon. And you get these this bead-like effect, and that's called Bailey's beads, after the guy in 1836 that first noticed them. So it's a way of mapping the lunar valleys to great precision, if you're interested in that approach. And also it is a good measure of libration. You know, the moon is tidally locked so that one side always faces the Earth, but it's rocking a little, and it librates about 7 degrees. And this is a good way to measure lunar libration very precisely. So that's an example of Bailey's bead science. The diamond ring effect is just before the sun disappears, it looks like that. And just before it reappears, it makes another diamond ring effect. And that's kind of, it looks like an explosion. Every time I see after a total solar eclipse, when I see the diamond ring effect, it strikes me as an explosion on the moon that then engulfs us all. During totality, animals go to sleep and other things happen, and you just feel like the whole world has wound down. And it seems like it's going winding up again when you get the diamond ring effect, and suddenly you're engulfed in the sun and everything's back to normal, but you're not. I've tried an experiment. I led an eclipse expedition in 1991 down to Baja with 2 buses and 91 people. That would take a talk too. But we had 50 people on this experiment. They're called the shadow banditos. And our experiment was basically to measure shadow bands. And no one's gotten a good picture of shadow bands. If you want to be famous, everybody thinks they can get it before the eclipse. Every single expedition I've ever been on for solar eclipses, everybody thinks they can do it. No, nobody else has done it in 100 years, and they never do because the contrast is less than 1%. So this is a drawing of shadow bands. When you see a star, it sparkles because it's like we're at the bottom of a swimming pool, and you watch a person, they'll sparkle too. Or if a person's holding up a light or a match, and you're at the bottom of a swimming pool, you watch them, this light on the match will hop around. And that's just because you're at the bottom of a swimming pool and the light is getting refracted as the surface changes. Well, this happens as the moon covers up the sun becomes small enough in this direction that it starts to sparkle in that direction. So you have the slit like this of the sun, but it's so thin here that it starts to sparkle. What causes it to sparkle are the turbulent air cells that are closest to you. As it gets thinner, the higher up, less angular sized turbulent air cells start to contribute. And higher up still, you get another contribution. So it looks like there are a whole bunch of, it looks like 1 million butterflies is flying between you and the sun. and they're all fluttering, and the fluttering gets faster and faster and faster as the higher components of the air contribute to the diffraction pattern, and eventually then you get totality. So this is a phenomenon a lot of people miss because they're looking up. And you should look down. You could look across as the shadow of the moon approaches at 1,000 miles an hour. That's neat to see. You don't want to miss the stars appearing, but you don't want to miss shadow bands either. But anyway, the bottom line is if you can get a picture of a shadow band, it'll make the cover of Sky and Telescope. Okay, sometimes you can see the moon shadow approaching across the landscape, and this is a satellite picture of a total solar eclipse as the shadow moves across the Earth. Now, people have been watching eclipses for thousands of years, but we discovered a new eclipse effect. In 2002, the eclipse was in Australia, out in the outback in Australia, and we watched, and the eclipse finished, and everybody starts packing up, but I decided to keep looking. And all of a sudden, this isn't a very good picture of it, because it was really more like this big, but this is the first picture I could get of it. You know, you fumble around and you try and get your camera out, and by the time you get the picture, the effect has mostly gone away. But there was about this big emerald glow around the moon. And keeping Eddie Frank, the guy I go to eclipses with, the guy that organizes it, we decided we'd call it the Emerald Tiara effect. And I didn't know what it was. I remember thinking, you know, what the heck is that? And I had everybody come back, and I thought, is my telescope, my solar filter doing this? What is doing this? And so we got written up in Sky and Telescope. I wrote them a little note, and Steve O'Meara wrote a whole article. And I guess he quoted me here. He says, what the heck is that? So, and he talked about yellow Volkswagens. And he says, nobody notices them until somebody says, have you seen a yellow Volkswagen today? And now everybody goes, oh, there they are. Well, since 2002, everybody spotted it. So what's the lesson here? The reason I'm making a little bit of a big deal is, the lesson here is you can look at a scientific phenomena that thousands of people or millions of people have looked at for thousands of years and still discover something new. And now everybody sees it. It's not like it doesn't occur on every low solar eclipse. So, you know, there's lots of science even where it should be so obvious there's nothing new to discover. Another thing you can study during solar eclipses are solar prominences. And those are twisted magnetic field lines of the sun. And they're really beautiful. When you get to totality, you realize that the solar prominences are colored scarlet. So during totality, you see these scarlet twirls coming off the sun. It's really gorgeous. Another thing is you can study the solar chromosphere. And this is called a flash spectrum. And basically what happens is as the moon covers up the sun, there's a thin layer of the outer part of the sun above the photosphere that has some unique properties and lots of color, and it's called a chromosphere. And if you're taking a spectra of the sun during total solar eclipse, you get this sudden flash of emission lines. And that's straight from the chromosphere. And this is one of the few ways to actually study the chromosphere of the sun. And we know chromospheric activity is important because it's related to star spots and sunspots. And we know sunspots are of interest because, for example, during the Maunder minimum in the Middle Ages, actually a little later, the Maunder minimum of sunspots, and those sunspots appeared, may have been related or appears to be related to the mini ice age. So this is a good place to study, you might say, effects of the sun on long-term climate. Okay. Sunspots are the best refrigerators in the solar system. Even though they're on the sun, they're 2,000 degrees cooler than the solar surface. The sun is a dwarf star, and it's basically equivalent to about 80 billion hydrogen bombs exploding every second. So if you explode a hydrogen bomb 1 a second for 3,200 years, that's how many hydrogen bombs the sun explodes every second. And it's a dwarf star. it makes the Earth look little. About 1 million Earths would fit inside the sun, but about 100 million suns would fit inside Betelgeuse, the star Betelgeuse. And of course, everything depends on the sun. All energy comes from the sun directly or indirectly. And I was interested to find out that photosynthetic systems, in a recent Nature article, that leaves are quantum computers, that the photosynthetic activity that is the basis of life on Earth is actually based on a quantum effect. Quantum computers are computers that do all the calculations more or less at the same time, and then the solution collapses out. So it's the kind of ultimate parallel processing. And it's what can explain the efficiency of life on Earth, of photosynthesis. If you look at the genetic structure of plants, this is another talk too, it's more complex. Now, why would plants be more complex than humans genetically? Well, because they make their food and eat it, whereas we just eat. If you have to make your food and eat it, you're intrinsically more complex being. So I'll just throw that out there. Trees are also 90% of the land biomass, and they somewhat control the weather. And anyway, if you want to talk about the dominant species on Earth, you'd have to say trees and their dependents. If you were an alien, you'd be 90% right, it's trees. Well, that's not to exclude these guys as trees. In this case, when they photosynthesize, the oxygen tends to bubble away, so they don't use it again. So actually, the source of our oxygen, the largest source of our oxygen, is probably sea plants. But anyway, all this depends on the sun. So studying the sun is important. Now, the moon is probably the Earth's primary clock. This is just a real quick example, but as we know, everything's run by a lunar cycle, pretty much. Also, we know that the moon stabilizes the Earth's rotation axis. The Earth's rotation axis could flip chaotically like Mars does if it weren't for the moon stabilizing it. So as far as SETI goes, you need a moon to have a habitable planet. Well, there's two reasons that's probably not the case. One is if you put the moon back into the Earth, it would rotate fast enough to stabilize itself. So if you remove the moon, in other words, you get stability either way. The other thing is if you flip the Earth, it would be unpleasant, but it wouldn't cause the extinction of life on Earth unless we had a polar continent. If Pangaea happened again and the Earth flipped in such a way that Pangaea was a pole, then we'd be up the creek. So don't put all your eggs in one continent basket and we're okay. Okay, now I'll talk a little bit about eclipses. There is a reference to Hai and Ho failing to predict an eclipse in 2136 BC. This is the actual eclipse, and the fact that there's a Chinese record expecting these guys not to, and they didn't, so they were hung, indicates that the Chinese routinely expected to be able to predict eclipses in the 3rd millennium BC. Here's an eclipse mentioned in the Odyssey, 1178 BC. I can discuss more of these if you have a favorite. There was a Chinese double dawn eclipse, which certainly was predicted and well recorded. The Chinese have the best eclipse records of any folks. About half the scientific records are Chinese, I'd say. But this is the guy we usually give credit to in our textbooks. Tales of Miletus predicting the eclipse for May 28, 584 BC. And it stopped a war. I'll talk about that in a second. There's the crucifixion of Jesus eclipse in 29 AD, but trying to explain, it doesn't say in the Bible that it got dark for 5 minutes. Longest eclipse we can have on Earth is 7 minutes, 9 seconds. So not sure how that can explain that everything got dark for, what was it, half a day or something, several hours. Anyway, prominences are first described as early as 334 AD. And a comet was first discovered during the eclipse in 418 AD. And this is a famous eclipse, Muhammad's birth. This eclipse foresaw the birth of Muhammad. And the first description of the corona, you'd think, well, does that go back? Yeah, it goes back over 1,000 years. And then there's the visit to Genghis Khan eclipse, which I'll go into in some detail, and show a modern scientific conclusion that was derived from this ancient eclipse. First, Talza Miletus foretells the eclipse. There's this 5-year battle between the Lydians and the Medes. That's a Lydian, that's a Mede. Those are Medes. And they were fighting, and Herodotus, the famous historian, said, so when the Lydians and Medes saw the day turn to night, they ceased from fighting, and both were the more zealous to make peace. How many people have been to a solar eclipse? So you know it's awe-inspiring, huh? It's the safest, amazing thing nature does. I think it's the most amazing thing nature does that's safe. I've seen tidal waves, I've seen tornadoes, I've seen earthquakes, and eclipses are more dramatic. This lady said, I can't make the eclipse. Is there anything you can do? I'm busy in June. I said, I wrote her back and I said, well, if we took all the nuclear weapons and exploded them on the moon, we could make a crater deep enough to delay the eclipse by about a quarter second. Does that help? It's like it's this completely uncontrollable thing that's perfectly safe but perfectly amazing. And I'll tell you, the Mongolians, Genghis Khan's word for God was the eternal blue sky, and things are important to the Mongolians that happen in the sky. And they were, well, anyway, I'm getting ahead of myself. Okay, well, anyway, this is the best documented battle in ancient times because we know when the eclipse occurred. So eclipses can also be used as to date historic events. I don't want to leave out the Maya. This is an eclipse. It's digitized pretty badly, but anyway, this is eclipse tables that are found in the Dresden Codex. The thousands of books were burnt by the Spanish conquistadors, and this one priest said, they look so sad as we burnt their books, which were obviously the work of the devil. Well, they weren't. They independently invented the zero. They had a base 20 system because they didn't wear shoes. They wore sandals. So they counted 20 digits. And they basically left, the only calculations we really have beside the Dresden Codex is on this stela, this 30-foot stela. See, here's a person in Copan. On the sides of this are eclipse calculations going back 400 million years. So they had the accuracy. Everything was revolving around Venus, the synodic period of Venus, which is 594 days. And they had the synodic period of Venus down to 14 seconds. And this is before the telescope, of course. So they're the best astronomers till the mid-1800s, I would say. And if you're a conquistador and you're using Roman numerals, you haven't got a chance against the Maya mathematicians. Okay, here's some more recent eclipses. As you probably know, Captain Cook was not sent to discover Antarctica or Hawaii because he hadn't discovered it yet. He was sent to observe a transit of Venus. So that was his main commission. And they wanted to observe a transit of Venus because that gives you the distance to the sun. So he could calibrate, once he knew the distance of Venus to the sun, they could get the true distance of the sun from the Earth. So while he was there, of course, he discovered a bunch of things and stuff, and that's usually what's written up. But the fact is he was sent there for an astronomical reason. Tecumseh was the Genghis Khan of, or could have been the Genghis Khan of the Native Americans. He was uniting tribes to stop the outward push of settlers. And his brother, I don't know exactly how to pronounce it, but Tenskwatawa, he predicted, General Harrison, who was soon to become President Harrison, was in a public assembly in a Native American meeting, and he challenged Tenskwatawa to predict something, because he was supposed to be a prophet. And he suggested an eclipse. Well, Tenskwatawa nailed it, June 16th, 1806. So that was to the discredit of General Harrison, and of course this caused a big following of Tecumseh. So Tecumseh was Shawnee, but he was uniting all the Native American tribes, and if he had succeeded, history would have been a lot different. Bailey's beads are first described, as we mentioned. The first photograph, a daguerreotype, was in 1860. So an eclipse was, this is within, let's see, photography was invented in 1839. So that's very close to the invention. There was an annual eclipse, the Battle of Asandluana. The British were fighting the Zulu, and the Zulu beat them up. They were actually not afraid of the eclipse. They actually caught, when the eclipse occurred, they took that as an omen of their victory. There's a story of the guy being eaten by, I don't know if I should tell jokes, but anyway, there's a story of a guy that's in a pot being eaten by cannibals, and it's getting hot, and he's worried, and he goes, wait a second, there's a solar eclipse today. I'll tell them I'll block out the sun, and they'll let me go. So one of the natives dances nearby, and he says, when are you going to eat me? And the native said, right after the eclipse. So don't underestimate the locals. And then, of course, the Einstein-Eddington eclipse, which confirmed general relativity, and this made Einstein famous overnight, and that was in 1919. And up until SETI at home, I think this was the largest science experiment ever done. It turned out there was a solar eclipse over New York City, January 24th, 1925, and they got everybody in New York City to note what they saw. And it turned out that, I think it was between 31st Street and 32nd Street was the dividing line between when the eclipse could be seen as total and when it wasn't seen as total. So they really nailed the edge for the first time. And they estimated about 1 million people participated. And finally, this one's notable. This is a jet over the Kenya 1973 eclipse, where they used the Kuiper Airborne Observatory, and they set the record of 76-minute long eclipse. Okay, just a little review. Basically, if you look at two stars and their separation, and you note that, then the sun comes in between. If the sun's bending the light, they'll look like they're farther apart than they were. And that was a very hard measurement to do. Eddington went I think he went to Brazil to try it the first time, and then he finally succeeded in measuring it off the coast of Africa. But his precision wasn't enough to really claim that it happened, although he gets credit for it. The folks at Lick Observatory were the real ones that nailed it. But Eddington believed Einstein and basically said, I support Einstein, and that's when he became famous. But the actual data was taken at Lick Observatory at the following eclipse that could show error bars that said, yes, Einstein really was right. Of course, this led to cosmology. So without that exact fit of the moon over the sun, modern cosmology may not have kicked off yet. There's the actual plate. So you can see how difficult it was to do this measurement. Okay. Some eclipse science is that ancient historic eclipses can determine changes in the Earth's rotation rate. The Earth is slowing down, everybody's dragging their feet. And eventually that adds up, but not as much as all the round pebbles in the Bering Sea. If you see a pebble that's rounded in a river, it's because the river has had a frictional interaction with it. And mostly the Bering Sea, as the Earth rotates, the shallow seas slow it down. So it can be used in many aspects of the sun. The element helium was discovered in solar eclipses. General theory of relativity was discovered. And lots of science is going on today, especially with coronal streamers, Wilson depressions, and so on, mostly having to do with sunspot cycles. We like to know if the sun's going into a Maunder minimum so we can get ready for an ice age. Okay, this is a Babylonian eclipse that illustrates how the Earth's rotation can be measured using eclipses. This is 136 BC, and it should have happened here. But the Babylonians said we saw an eclipse. How can that happen if the eclipse track was here? Well, it means that the Earth was going faster, and east had already gotten under the path. So the change in time delta t is not 0, or the Babylonians would not have had an eclipse. So the Earth was able to rotate faster and scoot them under the path. So that's one of the earliest measurements of that. Oh, that's wrong. Direction of the Earth's rotation is that way. Okay. And here's basically the mathematics, the cuneiform. They used base 60. The Babylonians used base 60 in their calculations because they had 60. No, because no, I think that theory. Because it's divisible. They didn't have decimal points, so it's divisible by 1, 2, 3, 4, 6, 10, 5, yeah, 10, 12, 15, and so on. So anyway, if you have fractions, base 60 makes sense. And of course, we still use it today because with time. The reason we do time base 60 isn't 72 after or something is because the Babylonians. We also use it in our coordinate systems, 360 degrees and so on. So that's I guess timekeeping systems are really tenacious in cultures. We have almost a completely uniform timekeeping system on Earth left over from thousands of years ago. But this I'll go into a little more detail with this guy. Is everybody doing okay? Okay. A Taoist leader named Chang Chun is summoned in 1220 to visit Genghis Khan. He sees a total solar eclipse in Mongolia on the way, and he adds an important point to the calculation of the slowdown. There's Chang Chun there and his astronomical stuff. He knew to keep track of the time and so on when the solar eclipse occurred. Now he was traveling from China to Mongolia, and he saw the eclipse at this river here. And basically, remember the delta t? That can't be 0. The best fit is a delta t of 840 second lag in the Earth's rotation. So here's an article on discussing. Basically, this gentleman is a historian, a Chinese historian, and this gentleman's an astrophysicist, a geophysicist actually. So they're collaborating a lot because the Chinese records are the best. And basically, Cheng Chun wrote in the spring AD of 1221, this is his student writing about him. Cheng Chun began a journey from northeastern China to Samarkand, having been summoned by Genghis Khan. And they were camped on the Kurlan River, somewhere around here. And just to point it out, I don't have a pointer, but basically, if t was 0, you'd have to be up here. But he said we remained to the south of the river during the whole journey. So even if you go to this point, this is the 0 point for t equals 0. So he couldn't have seen a total solar eclipse, but yet he says the stars came out. So he wrote, his party proceeded in a roughly northern direction in order to visit Prince Temuga, who is Genghis Khan's youngest brother. On May 15th, he reached Lake Hulun at a place where the river Karelin overflows. On the first day of the 5th month, at noon, the sun was eclipsed and it was total. All the stars were then seen. Now that shows that definitely it was total. A short while later, the brightness returned. That time we were on the southern bank of the river. The eclipse began at the southwest, reappearing in the northeast. So even if we allow for barely being south of the river, we still need t to be at least 555 seconds. So it's probably the best fit is around here for various reasons that are historic. So basically, they concluded that the rotation of the Earth is slowing down by about 1.6 milliseconds per century. Okay, you have to take into account a bunch of things, the eccentricity of the Earth's orbit and so on. So that means the dinosaurs had a 21-hour day, and that the Earth probably started out with a 5 or 6 hour day. And so you can look at the ancient Babylonian observations and the Greek observations, and also a lot of the Chinese and more modern Arab, and you can fit them with a curve and get the rate of slowdown of 1.6 milliseconds per year. So this is an example of eclipse science you can get. Now this is, this is kind of the relaxed part. I want to share just a bit of Mongolia with you. When you arrive at Genghis Khan International Airport in Ulaanbaatar, you see "Welcome to Mongolia," and and you see a bunch of Genghis Khan soldiers and various khans, and their murals on the wall that say "Celebrating 800 years of the Mongol Empire." Well, as we know, the Mongols took 25 years to conquer an area twice the size of the Roman Empire, which took them 400 years to do. They had bows that would penetrate the armor of the day, the European armor, because they were backbent bows. And for their own armor, they wore silk shirts. And the reason silk worked is when an arrow comes in, the silk wraps around it. So they didn't have to push the arrow through. It's kind of gruesome, but they could pop the arrow out. So it wasn't critical. It was painful, but it wasn't critical. So here was our eclipse camp. The eclipse happened right up there. And here's our camp. I took this picture because there's a sundog. And here's where we lived. And Mongolia is an area of rolling hills and all. And if I was going to start a business, I would start a hovercraft business because Mongolia doesn't have any roads. So now's a good time to do hovercraft. I mean, it's like Africa will never put up telephone poles, right? They jump that technology. Well, I think they could jump the highway technology in Mongolia. And this eagle kept hanging around before the eclipse, which is considered a great omen by the Mongols. These are yurts, or they're called gurs in Mongolia, Kazakhstan, where the Cossacks come from. They're called yurts. But these gurs are permanently inhabited, but they move around, and they follow the grazing yaks and stuff. So the whole country is this wild critters and wild horses and stuff, and rolling hills, and no fences anywhere. And the sky is very important. The people we worked with, we had 37 people to take care of a bunch of us, and they were told by the elders to go into the gurs, paint their faces black, and hit pots and pans. And I said, no, you don't want to miss this eclipse. It's beautiful. And they were like, well, okay, tell us about it. And I'm going, well, you know, the moon's going in front of the sun. And everybody started to get real uncomfortable in kind of a scared way. And then the moon completely covers the sun and the stars come out. And there were gasps at that point. It's like, no. And I'm going, yeah, the stars are going to come out. But I talked every one of them to come out and see the eclipse instead. So, of course, some people are looking through optics, so I had to count down from 10. So we practiced. Ready? 10, 9, 8. Everybody count with me. Okay, we're going to do it again. 10, 9, 8. Then I learned to count down from 10 in Mongolian for them. And then put your glasses on, your eclipse glasses, which everybody got. Well, the eclipse occurred, and our group is going, wow, look at that, yippee, yippee, as it begins to cover up the sun. And bless their hearts, the Mongolians are going like, so a totality occurred. The stars came out, more gasps. And then after totality, everybody came up and shook my hand like I had anything to do with it. That was the best eclipse. I was being congratulated. And everybody's crying. Even the men were crying. They were like, that was beautiful. We're so glad we did this. And it was like the most emotional eclipse by far I've ever been on. I've seen folks in Africa take off running down the street, but I've never seen this, like, tears and like congratulations. And they'll get a picture with a famous, you know. In Zambia, we had to go to Kafue National Park, and driving through it, there was two guys with machine guns that are supposed to guard the entrance to the park. They catch poachers and stuff. And they expect you to get out and talk with them for a while, because that's the way it is in Africa. So got out and chatted a little bit, and I said, by the way, this afternoon, you know, the eclipse, yeah, we heard about it. Your chickens are going to go into the roost in the middle of the day. And so, you know, they're like, okay. So we went to the eclipse. we came back, driving back into Kafui. We stopped, and they ran up to me and shook my hand and said, "The chickens did exactly what you said." So I have this great reputation as a chicken psychologist. If this astronomy gig doesn't work out, I've got a place. So there's a typical place in Mongolia. It's generally high, and there's lots of herds, and that's just where you live. And they can pick up these gurs in about half an hour and move them wherever. And they mostly ride horses. That's one of our trucks over there. We went by truck, but like I say, there aren't any roads. In the winter, of course, it gets to be minus 50. It's a very nippy place because, of course, there's no coastal area. And here's some Mongolian ladies that also are musicians, but during the summer, they work as tourist people. And you can see the Mongolian horses are much smaller than our horses, but they're strong. I mean, I could ride one, and that takes a strong horse. There's our camp back there, the yellow tents. Most hospitable people on the planet, I have to say, just unequivocally. They don't welcome you like it's an event. They just automatically, you're part of the family. They skip that whole big deal. They're just part of the family. And of course, they actually tame some golden eagles. We saw lots of golden eagles there. And let's see. They sing deeply in the throat. Throat singing, you probably heard it. Hear the whistle? That's his voice. And that are both the same person. Sorry about the wind. I didn't have time to correct it. They suppress the voice and all you can hear is the overtone. That's what you're hearing. Sing along, right. Sorry about the video. There's a horse on the instrument. Half the songs are about, I love my horse. I had a laugh after that. It was so weird. The throat singing, can you imagine the Mongols are attacking Europe and they're sitting around the campfire singing like this, and if there's any doubt they came from, the underworld, that pretty much removed it. So my last slide is basically to conclude that eclipses are great. Please see one if you can. The next one in the continental US will be 2017. There is one, but it's across near Tahiti this year on the 11th, I think, of July. Lots of science is still being done. Harvard folks were near an eclipse camp that we went to in Zambia, and they're doing 6 experiments. Totality will happen very quickly. You hand out a piece of paper to take scientific results, and you get that. There was a guy in one of our eclipses that said, I'm going to record my response so that I don't take my eyes off the phenomena. And so he started a recorder going, and the eclipse lasted for several minutes. It was a rather long one. And afterward, we listened to his recorder, and it said, "Oh, wow. Oh, Wow, look at that. Oh my gosh, look at that. Oh my, there's not one quantitative statement. So don't expect to get, it's very hard to get data during totality. Things go nonlinear quickly. On the shadow band experiment, 1/4 of the people forgot to take the lens cap off. And we'd practiced for days. So anyway, maybe enjoy the first eclipse and then steel yourself to ones after that. So, questions?
That's great. Thank you. That was a really fun talk. We'll have a personal demonstration of throat singing right at the end.
Oh, all right. I'm still working on that, but
Let me just start with one question. So with the experiment with the Genghis Khan eclipse, where they were trying to precisely locate the eclipse timing basically based on the location of this river, wouldn't the river have moved somewhat? I mean, is the motion of the river small compared to the locations you're looking at? That's just a work, yeah.
That's a good point. This is one of the few cases where the river hadn't moved in the 700 years.
Okay.
800 years. So yeah, that worked out really well. That was one of the things they checked.
Okay.
Good point.
So, other questions?
I was wondering if the emerald tiara effect that you talked about is related to the green flash phenomenon that we see.
Good question. It is. It is related to the green flash, because the green flash is a diffraction effect where the green light isn't bent as much as the blue light and bends more than the red light. So you actually have two images of the sun coming through the atmosphere, and when the image you see sets, the green image is left. And that's if the atmosphere is pure enough and has a good enough single refractive index, then you can see a green flash. And that's exactly what's happening. The emerald tiara doesn't work below about 15 degrees. So it's similar, very similar. If you want an article on it, it's in Sky and Tell, and I'm happy to mail it to you. Send me an email and I'll mail you the article from Sky and Tell. Thanks.
I agree with you that solar eclipses are the greatest natural phenomena. I was wondering if you could think of anything relating them to what I think is the second greatest natural phenomena, which is the aurora. One of the times I saw a partial, it was a mid-70s partial, independent of the total I saw. I was down in McMurdo, which is latitude 77, and I was wondering, unfortunately, because we didn't have totality, if people had ever commented about aurora in the high latitudes during eclipses.
Oh, that's interesting. I don't know any correlation that's been specifically made between the two. That's pretty interesting. So the aurora is due to the solar wind being channeled down through the magnetic field. And as I understand it, they recently found the cause of the aurora's variation is due to the fact the solar wind's pushing back the magnetic field of the Earth, and it gets to a certain maximum point and snaps back and wiggles, and that causes the aurora. But during totality, how does the moon affect the solar wind hitting the Earth? That's an interesting idea.
Oh, I mean, even just simply seeing an aurora during, as opposed to other astronomical,
okay,
such as stars.
Yeah, I don't know any, but I'd be interested if you do know anybody pursuing that. That's very interesting. That's very cool.
For those of you who want to go to an eclipse, there is the July 11th eclipse this year, not too long ago in the future. SETI Institute is actually a partial sponsor of 2 trips. You can find information on our website. One of them is one of them that will take place on a cruise ship in the Marquesas Islands near Tahiti. That's a very beautiful trip where you visit many of the Marquesas Islands and see the eclipse. And the other one goes to Patagonia in Argentina, and Seth Shostak is going to be the lecturer on that trip. And Patagonia is very interesting too. And that's, by the way, a very long eclipse. I think it's a 5-minute eclipse.
Yeah, it's 5 minutes, a little over 5 minutes. The other neat thing is I assume that in the Polynesian one, you'll be discussing Polynesian astronomy and all that. It's a great place to have an eclipse because you can discuss, the Polynesians were the best. Being a Viking, I hate to say it, but the Polynesians were the best navigators.
Great. Other questions? Comments?
Yeah, and all of these historic measurements of the Earth's rotation speed, can I assume that they've also factored in movements of the continents, continental drift?
Well, yeah, that's a good point. The eclipse effect is a lot larger than the continental drift, but when you're measuring things like the distance to the moon, the fact the moon's moving out an inch a year, then you have to take that into account. But for eclipses, like you saw even a couple thousand years ago, 3,000 years ago, an eclipse was supposed to have occurred, which occurred over Babylon, was supposed to have occurred, 1,000 miles away. So it's a much larger effect. But that's a good point. I assume so, but they didn't say so specifically in the paper about the Genghis Khan eclipse. Maybe 700 years isn't a large enough baseline to have to require that. All good points, though. When the moon's overhead, the Earth is 6 inches higher. So you have to take these sort of things into account, too. It bulges when the moon's overhead.
So you mentioned there will be an eclipse in North America in 2017. Can you say more about where and when?
I don't have the data with me right now. I just noted that was it. But okay. But yeah, definitely, if you can see a solar eclipse, I definitely would. It's definitely worthwhile. It's a unique present of our age, This doesn't happen. It hasn't happened for the dinosaurs or anything, so.
Other questions? Great. Let's thank Laurance again.
Thanks.